Hello everyone, welcome back to my channel, or welcome to my channel if it's your first time watching. This is very monumental for me as it's the last GCSE video I'll be doing for a while now. So I hope you all enjoy this very much. I hope this is useful. It's covering physics paper 2, higher combined, so no physics, only content, no triple. And there is some stuff that, foundation stuff is in it, but it's for higher combined AQA. Okay, thank you, let's go into the video. So on to topic 5, the first topic, forces. Vectors have direction and magnitude.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Vector quantities include force, velocity, displacement, acceleration, momentum, etc. Scalar quantities include speed, distance, mass, temperature, time, etc. A force is a push or pull that acts on an object due to the interaction with another object. All forces between objects are either non-contact or contact. Non-contact forces would be electrostatic. The charges cause a force of attraction or repulsion, or gravitational attraction. The mass creates a force of attraction. A contact force would be a regular contact, if an object touches another object, or friction. All matter has a gravitational field strength and attracts all other matter. The larger the mass, the stronger the field, the greater the attraction. Weight is the force exerted on a mass by the gravitational field in Newton. The unit for gravitational field strength is newtons per kilogram. So remember the gravitational field strength of the Earth, unless it tells you otherwise, it will always be 9.8, as that's the gravitational field strength of the Earth. Unless it tells you to use 10 or any other value, just always use 9.8. The unit for weight is newtons and the unit for mass is kilograms. So the equation is weight equals mass times gravitational field strength. So you will be given that. This one says 10 here, but you should use 9.8. You'll be given this on the equation sheet. However, it is good to know as you want to apply it to some practice. Resultant force. This is a single object representing the sum of all the forces acting on an object. If more than one force act along a straight line, the resultant can be found by adding, acting in the same direction, or subtracting, acting in opposite directions. Okay, so here we have an example. If the air drag is 135 newtons, which is pulling him up as he's going a bit slower, and if the weight is 735 newtons, so that's pulling him down, the weight outweighs the air drag. However, the air drag still has an effect, so we just do 735 take away 135, and you get 600 newtons as your resultant force. And it's the same thing for this car here. The resultant force up and down is the same, so you just get 0 newtons. However, there's a bit of air drag back here, so 20 newtons, but the driving force is forward, so it's 100 newtons. So then you do 100, take away 20, so then you get 80. You always do the larger one, take away the smaller one. So resolving forces. So what you're going to do is you use the angle of the line to do these equations. It's maths. It's like a mixture of Pythagoras or cosine rule, depending on what values you're given. And yeah, so here they're using sine or cosine, not cosine rule, sorry, I'm so sorry, SOHCAHTOA. We have so the sine of 40 equals the vertical length over 60 newtons. So work done, the units are joules, for the force, newtons, distance, meters. So work done equals force times distance. This will also be on your equation sheet, however it's good to know once again. Springs. To stretch, bend or compress an object, more than one force has to be applied. If a single force is applied to an object, it will just move in that direction. If it is pulled in opposite directions on either side of the object, it will stretch. Deformation. This means changing shape. Elastic deformation is when the object returns to its original shape when the load has been removed. For example, an elastic band. Plastic or inelastic deformation is when the object does not return to its original shape when the load has been removed. For example, a spring when pulled too far. If you've ever pulled the spring out of a pen and you've pulled it, you'll notice when you've pulled it too far, it will just stay as it is and it won't spring back. So that is inelastic deformation. Hooke's law is the extension of an elastic object, such as a spring, is directly proportional to the force applied, provided that the limit of the proportionality is not exceeded. So the units for this equation is F is force applied to a string in newtons, K is the spring constant in this, and X is the extension in meters. More work done. When a force stretches or compresses a spring does work. Elastic potential energy is stored in the spring, provided it does not inelastically deform. The work done on the spring equals the elastic potential energy stored. So this is another equation for work done. It's the same units as before, with the K being the spring constant and the X being the extension. So you do it in meters squared, because it's x squared here and half. So distance is how far an object moves. Distance does not involve direction, and distance is a scalar quantity. Displacement includes both the distance an object moves, measured in a straight line from the start point to the niche point, and the direction of the straight line. Displacement is a vector quantity. Speed does not involve direction. Speed is a scalar quantity. Velocity, which is a vector quantity, is a speed in a given direction. So speed on its own is just a scalar quantity with no direction, it's just a speed. And velocity, when given the direction, the speed becomes the velocity. And here, everyone knows this, it will be on your equation sheet. Speed equals distance over time. So some displacement time graphs. The gradient of it will be the velocity. Sharper gradients mean faster speed. Negative gradient is returning back to the starting point. Horizontal line means stationary. Zero distance means back to the starting point. And the area under the line, it just says nothing. I don't know. I guess it means nothing. The curved line means that the velocity is changing, the acceleration. If an object is accelerating, its speed can be determined by drawing a tangent and calculating the gradient of the distance time graph. So some velocity time graphs. The gradient is acceleration. The sharper the gradient means the greater the acceleration, and a negative gradient is deceleration. Horizontal line means constant speed. Zero velocity means that it's stationary. The area under the line equals the distance travelled. Sometimes counting the squares is the best method for a curved line. Curved line means that the acceleration is changing. Average speed. This is for when the speed changes during the motion. Use overall distances and timings to work out the average speed. Newton's first law is: an object has a constant velocity unless acted on by a resultant force. If a resultant force acts on the object, it will accelerate. Acceleration is change in velocity over time, so velocity will change. If no resultant force acts on the object and the object is stationary, it will remain stationary. Yet if the object is moving, it will continue to move at the same velocity. The tendency for objects to continue in uniform velocity or stay at rest is called inertia. So Newton's second law.
I'm trying to cook some food. Why ain't recommending me Diddy? God, it presents to you the downfall of Diddy. Bro, I'm over here trying to cook some meat and they showing me the meat master.
The acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass of the object. Force equals newtons. The unit for force, is newtons. And the mass unit is kilograms, and the acceleration unit is meters per second squared. So force equals mass times acceleration, or F equals ma. This will once again be on our equation sheet, but it's good to know. Inertia, the measure of how difficult it is to change the velocity of an object. Inertia mass equals force over acceleration. Newton's third law. Whenever two objects interact, the forces they exert on each other are both equal and opposite. So the force pushing forward, you will receive as it says here, forces always come in pairs. You push on a wall, the wall will push back onto you. Vehicle stopping distances. After seeing a hazard, before you react during reaction time, you travel x meters, thinking distance. Then you brake, causing the car to slow down and stop over y meters, the braking distance. So stopping distance equals thinking plus braking distances. So things that affect your thinking distance would be the speed that your car is already going. It will be affected by reaction time if you just react slow and naturally. Your concentration, how tired you are. If you're fatigued, you will not be able to react as quickly. Distractions, if your child is annoying you when you're driving, or like the influence of drugs or alcohol, which is why you're always advised not to drive under the influence. So things that can affect the braking distance would be factors such as speed as well. If your car is going too fast, you can't brake as fast. Poor road conditions, so if the road is icy or wet, you're not going to be able to slow as fast because the friction on the road. Low friction, as it says, bold tires. Worn brake pads, if your brakes aren't up to scratch, and weight. If there's more passengers, it will be more difficult to brake. So momentum is calculated by mass times velocity. So the unit for momentum, the unit for mass is kilograms, and the unit for velocity. So momentum is always conserved in a collision or explosion where there are no external forces like friction, air resistance, electrostatic attraction, etc. In collisions, the total momentum before equals the total momentum after. So two marbles colliding will each have momentum before and after the collision. So momentum is a vector. Topic 6, we're on to topic 6 already. We got waves. So wavelength is the distance between the same points on two consecutive waves. Amplitude is the distance from equilibrium line to the maximum displacement. Frequency is the number of waves that pass a single point per second, and period is the time taken for a whole wave to completely pass a single point. So period equals, the unit for period is seconds, the unit for frequency is hertz. Here is the equation, period equals 1 over frequency. So there's no unit for 1, it's just 1. And there's another one, which is frequency equals wave velocity over wavelength. So the types of waves, there are transverse waves, where light, which is light, or any electromagnetic wave having peaks and troughs. Vibrations are at right angles to the direction of travel. Longitudinal waves, sound waves, have compressions and refractions. Vibrations are in the same direction as the direction of travel. So to measuring velocity, you could first off, the sound and air, you could make a noise 50 meters from a solid wall and record time for the echo to be heard. Then you speed equals distance over time. Or you could have two microphones connected to a data logger at a large distance apart and record the time difference between a sound passing from one to the other. Then you can also use speed equals distance over time. So to measure the ripples on a water surface, you could use a stroboscope, which has the same frequency as the water waves. Then measure distance between the fixed ripples and use V equals, which is wave velocity equals frequency times the wavelength. As you can use that equation. And you can move a pencil along the paper at the same speed as the wavefront and measure the time taken to draw this line. Then use speed equals distance over time. So electromagnetic waves, this is the standard numbers for it. So radio waves is 10 to the 3, I think. I don't know if these are minuses or not, I can't really see properly. It's best you check, because I know that one's -8, I know that one's -10, that one's -12, but I can't really see for the other ones. So the wavelength, the electromagnetic waves, are radio waves. I don't know if you've listened to the electromagnetic wave song, we should give it a listen. You know, the radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-ray, gamma ray. There you go. So as you can see, the wavelength will be more coiled and shorter as you go further along. You know, the decreasing wavelength and increasing frequency as you go this way. So as speed is constant for all EM waves, as wavelength decreases, frequency must increase. As frequency increases, energy of the wave increases. Our retina can only detect visible light, a small part of the entire EM spectrum. This visible light is still an EM wave, like X-rays and microwaves. If entering a denser material, it bends towards the normal. So this is refraction, light. We were talking about light here. If entering a less dense material, it bends away from the normal. So substances will absorb, transmit, refract, or reflect certain EM waves depending on the wavelength. Glass will transmit or refract visible light, absorb UV radiation, reflect infrared radiation. The material interacts differently for different parts of EM spectrum because their wavelengths and frequencies are different. So you should remember how to do this in the exam. If the light goes this way, it will go back up and like that. So that's refraction. Some effects are due to differences in velocity. When light enters a denser medium, it slows down. Shorter wavelengths are slow down more than longer wavelengths. Blue light slows down more than red. Dispersion occurs of a white light into a prism because the different wavelengths refract a different amount and therefore spread out, creating a rainbow effect. When refracting, the speed decreases and the wavelength decreases too in denser materials. The horizontal lines show the wavelength of the waves. Imagine each line is a maxima of the transverse wave. So radio waves are produced by oscillations in electrical circuits. When radio waves are absorbed, they create an alternating current at the same frequency as the radio waves. So when electrons move to a higher orbit further from the nucleus, the atom has absorbed EM radiation. When the electrons fall to a lower orbit closer to the nucleus, the atoms have emitted EM radiation. If an electron gains enough energy, it can leave the atom to form an ion. So gamma rays originate from changes in the nucleus of an atom. So atoms and EM radiation. UV light, X-rays, and gamma have hazardous effects on human body tissue. The effects depend on the type of radiation and the size of the dose. Radiation dose is how much exposure leads to the harm for a person. UV rays can, it can make your skin age prematurely, increasing risk of skin cancer. So sun cream will prevent overexposure in the summer. X-ray and gamma rays are ionizing radiation that can cause the mutation of genes, thus also causing cancer. Minimal exposure to these rays should be ensured. So the uses of the EM waves is obviously radio waves you can use in TV and radio. The long wavelength can travel far without losing quality. So microwaves, satellite communication and cooking food. It can penetrate atmosphere to reach satellites. Infrared radiation, infrared rays, you can use also for cooking food and infrared cameras. So it transfers thermal energy. Visible light waves, fiber optics, best reflection, scattering in glass. Others have too short or too long wavelengths. UV rays are used in sun tanning, in tanning beds and stuff, and energy efficient lamps. It radiates the least heat but more energy. X-rays are used for medical imaging and treatment, as well as gamma rays, whereas they are very high in energy and can penetrate material easily. So topic 7, we're on to the last topic for combined higher. So there is another one if you're in triple, just to warn you again. It's not the end of the road for you. You're going to have to go see another video because this is for combined higher. Anyways, topic 7, magnetism and electromagnetism. So magnets, north and south poles, same poles repel, opposite poles attract. Permanent magnets, always magnetic, always have poles. Induced magnets, materials that are magnetic but do not have fixed poles. These can be made into temporary magnets by stroking them with a permanent magnet. These align the domains of the material all in the same direction, creating a temporary magnet. For example, iron, nickel, or cobalt. Magnetic field. Field lines point from north to south. Strength decreases with distance from the magnet. Direction always points to the south pole and away from the north pole at any point. Use plotting compasses, small compasses which show the direction of the magnetic field at a certain point. The Earth's core. The core is magnetic and creates a large magnetic field around the Earth. We know this because a freely suspended magnetic compass will align itself with the Earth's field lines and point north. Current. Current produces a magnetic field around the wire. The direction is dictated by the right-hand grip rule. Plotting compasses on a piece of paper through which a wire is pierced through shows this. The strength of the magnetic field. Greater current means stronger magnetic field, and greater distance from wire means a weaker field. So magnetic field shape is similar to a bar magnet. It enhances the magnetic effect as coiling the wire causes the field to align and form a giant single field, rather than lots of them all perpendicular to the direction of the current. Having an iron core in the center increases strength as it is easier for the magnetic field lines to pass through than air. Factors that affect the strength will include the size of the current, the length, the cross-sectional area, the number of turns, coils, and using a soft iron core. So the motor effect. Two magnets will interact, feeling a magnetic force of attraction or repulsion. So a man and a wire will also exert a force, as the two magnetic fields generated by the magnet and the current in the wire will also interact. The magnetic field around the wire is circular, but the magnetic field between two magnets is straight. When the two interact, the wire is pushed away from the field between the poles at right angles to the wire direction as the field direction and the field direction. To visualize, fixed permanent magnets have field lines along the x-axis as the magnets are at A and B, and the field lines are shown. The wire is along the y-axis where current is moving from C to D. The force felt along the wire is at right angles to both the direction of the current and the magnetic field lines along the z-axis. So Fleming's left-hand rule. Each direction is 90 degrees to each other. Use this to work out the unknown factor of the three, usually the direction of the force felt. Remember, current is conventional current, which moves in opposite direction to the electron. So here's your formula for that. Electric motors work in a specific way. Permanent magnets lie in fixed positions, in between a coil of current-carrying wires on an axis. Force on one side moves that side up, whereas force on the other side, where current is flowing in opposite direction, moves down. This can be verified using Fleming's left-hand rule. Hence it rotates. Thank you very much. So that's your entire paper 2 covered in 24 minutes. I know, I'm amazing, I'm the best. Thank you so much for watching. I hopefully have carried you to your 9s. Yeah, that's my last GCSE video for a while. You know, maybe next year I'll be back on the horse helping the next generation, but for now, thank you very much. Make sure to like, subscribe, and comment. And that emoji is disgusting. Oh god, that's ruined my life. Thank you guys so much. So much. Goodbye.